What if your life wasn't the only version of reality? What if somewhere out there, another you made different choices, chose a different career, married someone else, never existed at all? This isn't just a sci-fi fantasy. It's a serious question that some of the world's top physicists are beginning to consider. Welcome to the mind-bending world of parallel universes, alternate realities that may coexist alongside our own. The idea is so radical, so world-shattering, that if proven true, it could rewrite everything we think we know about existence. And the strangest part, the math might already support it. The story begins with a deceptively simple idea. The universe, as we experience it, may not be the only one. In fact, it may be just one bubble in a vast cosmic foam of infinite universes, each with its own laws of physics, its own histories, and its own versions of reality. This concept is known as the multiverse. But how did such a wild theory come to be? To understand that, we have to start with quantum mechanics, the science of the very small. At the subatomic level, particles don't behave like tiny billiard balls. Instead, they exist in a haze of probabilities. A single particle can spin clockwise and counterclockwise at the same time, or be in two places at once. This phenomenon is known as superposition, and it's been demonstrated in countless experiments. But here's the kicker. When we observe these particles, the superposition collapses into a single outcome. One result becomes real and all other possibilities vanish, or do they? This is where Hugh Everett comes in. In 1957, Everett proposed the many worlds interpretation of quantum mechanics. Instead of assuming that the wave function collapses into one reality, Everett suggested that all possible outcomes actually occur, each in its own branching universe. In one universe, the particle spins up. In another, it spins down. Both outcomes are real, but they happen in different branches of the multiverse. Every quantum decision, every event that could go multiple ways creates a fork, splitting reality into countless versions. At the time, Everett's idea was ignored, even mocked. It sounded like science fiction. But in the decades since, many physicists have begun to take it seriously. Why? Because it solves some deep paradoxes in quantum mechanics without adding any arbitrary rules. It treats the universe as a deterministic machine, but one that branches endlessly. The math works, the logic holds, and that's terrifying. Think about the implications. If the many worlds interpretation is correct, then there is a universe where you never watched this video, one where you never existed, one where Earth was never formed, and one where it was, but dinosaurs still rule it. These universes don't just exist somewhere far away. They exist in a higher dimensional space, layered over our own like invisible pages in a cosmic book. You can't see them, you can't touch them, but they're there, ghostly echoes of what could have been. And it's not just quantum mechanics pointing us toward parallel worlds. Cosmology, the study of the universe at large, also provides hints. According to the theory of cosmic inflation, our universe underwent a rapid expansion in the first tiny fraction of a second after the Big Bang. This inflation didn't just create our universe. It could have created an infinite number of bubble universes, each expanding separately, each with its own version of reality. This is called the level Y multiverse. In such a model, the observable universe we see is just a tiny patch of a much larger reality. But it gets even weirder. Some theories of string theory, a framework that attempts to unify all the forces of nature, predict the existence of multiple spatial dimensions beyond the three we know. These higher dimensions could host entire universes, each with different physical constants. In one universe, gravity might be stronger. In another, atoms might not form at all. And in one of them, life might have evolved in a completely alien way. Still, you might be asking, if parallel universes exist, why can't we see them? Why can't we interact with them? The short answer is maybe we can't. Most parallel universe models predict that these realities are causally disconnected from ours. They don't overlap in space and time in a way we can access, at least not with current technology. But there are anomalies that have intrigued scientists. For example, the cold spot in the cosmic microwave background, a region of space that is unusually empty and cold, has been speculated by some to be the result of another universe colliding with ours in the distant past. It's far from proof, but it's curious. Another area of interest is quantum computing. These exotic machines use quantum bits or qubits that exist in multiple states at once. Some researchers, most notably David Deutsch, have suggested that quantum computers might be tapping into the multiverse to perform calculations that would be impossible in a single universe. If that's true, then every time you run a quantum algorithm, you might be summoning the processing power of countless alternate realities. Of course, these are still theories. The multiverse remains one of the most controversial ideas in modern physics. Some critics argue it's unscientific because it can't be tested directly. Others say it's simply the most elegant explanation for the data we do have. It's a debate at the heart of science. Is a theory valid if it explains reality, even if we can't yet prove it? Or must we be able to observe and measure every claim? Regardless, the multiverse has captivated not just scientists, but philosophers, writers, and artists. Because it taps into something deep in the human psyche, the longing for possibility. The idea that somewhere, somehow, things could be different. That every decision spawns a new reality. That nothing is ever truly lost, just moved elsewhere. And perhaps that's the most profound implication of parallel universes. They don't just challenge our understanding of physics. They challenge our understanding of self. Who are you if infinite versions of you exist? What is choice if every option is eventually played out in some other world? These aren't just scientific questions. They're existential ones. So when you look in the mirror tomorrow, remember this. You're not alone. Not in the way you think. Somewhere, another you is making a different choice, living a different life, following a different path. And together, all those selves form a multiverse, a cosmic web of possibility, woven from the fabric of quantum reality. Welcome to the infinite. Let's go deeper. If parallel universes do exist, then how do they actually work? How are they created? How are they structured? And is there any way, any conceivable way, that we could ever detect or interact with them? To answer that, we need to explore the different levels of the multiverse proposed by physicist Max Tegmark. According to him, not all parallel universes are created equal. Some are simply distant regions of our own universe. Others are fundamentally different realms with entirely distinct physical laws. Tegmark categorized them into 4 levels, each more exotic than the last. Level Y is the simplest. It's the idea that space is so vast, possibly infinite, that if you go far enough, you'll eventually find a region that looks exactly like ours. Not just similar, but identical in every way. A planet like Earth with someone like you watching this exact video. This isn't science fiction. It's a consequence of the mathematics of probability. In an infinite universe, every possible arrangement of matter must occur somewhere, no matter how improbable. These universes don't have different laws of physics. They're just repetitions of our own, scattered across an unimaginably large space. Level 2 is more radical. This level arises from cosmic inflation theory, the idea that after the Big Bang, space underwent a brief but exponential expansion. During this inflation, different regions of space stopped inflating at different times, creating bubble universes. Each of these bubbles can have its own physical constants, particles and forces. In some, gravity might be weaker. In others, atoms might not even exist. We could never reach these other bubbles because the space between them is expanding faster than the speed of light. But theoretically, they're out there. Entire universes with different chemistry, different physics, and possibly different forms of life. Level 3 is the one we touched on earlier, the many worlds interpretation of quantum mechanics. In this level, every quantum event spawns a new universe. Every time an atom decays or doesn't decay, every time a photon takes path A or path B, reality splits. This means that parallel universes are constantly branching off from our own. There's a universe where you turned left instead of right this morning. One where you never went to school. One where Earth never formed. These universes coexist, not in distant space, but in a kind of quantum superposition, unreachable, but just as real. Level 4 is the most abstract. It proposes that every logically possible universe exists. Not just variations of our universe or even variations of physics, but completely different mathematical structures. A universe where time runs backward, one with 17 dimensions. One where cause and effect don't exist. If mathematics describes a consistent reality, then that reality exists somewhere in the level 4 multiverse. It's a staggering idea, essentially, that math isn't just a tool to describe reality. Math is reality. Now, this raises a critical question. If these universes exist, can we ever access them? Could we build a machine to travel between them? The short answer, based on our current understanding, is no. The barriers between universes, especially in level 2 and beyond, are either spatially unreachable or fundamentally disconnected. You can't fly to them. You can't send a message. They're causally sealed off. However, that hasn't stopped physicists from dreaming up ways to test the multiverse's existence indirectly. For instance, some cosmologists look at the cosmic microwave background radiation, the afterglow of the Big Bang, for anomalies that might suggest our universe bumped into another one. These might appear as circular patterns, cold spots, or gravitational distortions. So far, nothing conclusive has been found. But the data continues to improve. Others suggest that the behavior of quantum systems could hint at many worlds. The idea is that if every quantum event branches into a new universe, then the totality of all possible outcomes must be accounted for. Some physicists are working on mathematical models that might show this branching in subtle ways, though again, direct evidence remains elusive. There's also an argument to be made from the anthropic principle. The physical constants of our universe are finely tuned for life. Change gravity slightly, and stars don't form. Change the strong nuclear force, and atoms fall apart. Why are the constants just right for life to exist? One explanation is the multiverse. If countless universes exist, each with different laws, we just happen to live in the one where life is possible. It's not design, it's selection bias. We're here because we can be. Still, this line of reasoning is controversial. Critics argue that the multiverse is untestable and therefore unscientific. After all, science is built on falsifiability, the idea that a theory must be capable of being proven wrong. If we can't interact with or detect other universes, how can we ever know they exist? This tension lies at the heart of the multiverse debate. Is it physics or philosophy? Some suggest that the multiverse is like the horizon. We can't see beyond it, but we know it's there because everything we do see points toward it. The equations of quantum mechanics, the structure of the cosmos, the logic of inflation, they all hint at something more. Maybe we'll never see another universe, but maybe, just maybe, we'll find evidence written in the patterns of our own. Interestingly, this idea isn't new. Philosophers have speculated about multiple realities for centuries. In ancient Greece, the atomists imagined an infinite number of worlds. In the 17th century, Giordano Bruno proposed a universe filled with countless suns and planets, each with their own beings. He was burned at the stake for saying so. Today, those same ideas are echoed in modern physics, not as heresy, but as hypothesis. The multiverse also resonates with something deeply human, the desire for redemption, for second chances, for what might have been. In literature and film, alternate realities allow characters to rewrite their pasts, undo tragedies, explore possibilities. But what if that's not just fiction? What if in some corner of the multiverse those possibilities are real? And this brings us to a profound thought. If parallel universes exist, then everything you've ever imagined, every dream, every fear, might actually happen somewhere. You become not just the sum of your choices, but a node in an infinite web of realities. Your life, unique and meaningful, is also just one strand in a cosmic tapestry beyond comprehension. So what does this mean for you, sitting here in this universe? It means you are part of something bigger, much bigger. It means your decisions matter, because in this world, they're the only ones that count. In a sea of infinite possibilities, you are the observer, the chooser, the creator of your branch. And that perhaps is the greatest truth of all. If parallel universes are real, then how close are we to actually proving their existence? What would it take for science to confirm that we are just one of countless realities? And perhaps more intriguingly, could we ever reach out and touch another universe? Let's start with the question of proof. When scientists seek to validate a theory, they look for testable predictions, effects that can be measured, repeated, and confirmed. But in the case of parallel universes, we hit a wall. These other realities, by their very nature, are outside our observable universe. They don't emit light, don't interact with our matter, and don't leave traces we can detect with current instruments. So the first challenge is, how do you find something that, by definition, doesn't exist in your own space-time? One of the most serious attempts to find evidence involves the cosmic microwave background, CMB, the faint afterglow of the Big Bang. Some physicists believe that if our universe ever collided with another bubble universe from level 2, it might leave a bruise, a circular imprint or temperature anomaly in the CMB. Researchers have combed through satellite data from missions like WMAP and Planck, searching for these signs. A few oddities have been found, like the so-called cold spot, but none have provided definitive proof. For now, the data remains inconclusive. Another approach is more philosophical, the anthropic principle. If the constants of our universe appear fine-tuned for life, that could be because we exist in a multiverse where all possibilities are realized. In other words, we live in this universe because it supports life. It's not that the universe was made for us, but rather that we're only capable of observing the one that works. This logic, while compelling, is hard to test. It doesn't predict new phenomena, it just explains what we already see. So what about the many worlds interpretation of quantum mechanics? This idea that every possible quantum outcome spawns a new universe is not a fringe theory. It was first proposed by Hugh Everett in 1957 and has since gained support among many physicists. According to this view, the universe splits whenever a quantum decision occurs. Right now, there's a universe where you paused this video and one where you didn't. But again, how do we test this? One proposal is through quantum computing. If many worlds is correct, then quantum computers might be leveraging parallel universes to perform calculations. That sounds outrageous, but it's a serious line of thought. Quantum algorithms like Shor's and Grover's work exponentially faster than classical algorithms. Some physicists argue that this speed-up implies interference from parallel branches of reality. If we can better understand how quantum entanglement and superposition work, we might uncover hints of these alternate worlds hiding beneath our equations. There's also speculation about using gravity to detect other universes. Gravity, unlike the other fundamental forces, is incredibly weak. Some theorists believe this might be because it leaks into other dimensions, possibly into neighboring universes. Experiments using torsion balances and atom interferometers have tried to detect such leakage, but so far, results have been negative. Still, the idea remains tantalizing. Now, let's entertain a more speculative notion. Could a black hole be a gateway to another universe? This idea stems from the equations of general relativity. When a massive star collapses into a black hole, it creates a singularity, a point of infinite density. The math suggests that this point might be connected to a white hole somewhere else, a region where matter is ejected rather than sucked in. The theoretical tunnel between them is called a wormhole. If stable, such a structure could connect two distant parts of our universe, or two entirely different universes. The problem is stability. Wormholes, as predicted, would collapse instantly unless held open by exotic matter with negative energy, a substance we've never observed. Even if they did exist, the tidal forces near the singularity would tear apart anything trying to pass through. But in theory, they offer a potential bridge, a literal tunnel through the multiverse. So why do these ideas persist, even with little hard evidence? Partly because they offer solutions to deep problems in physics. The multiverse could help resolve the measurement problem in quantum mechanics, why we see a single outcome instead of all possible ones. It could explain why the cosmological constant, which drives the expansion of the universe, is so small. It even helps with the so-called fine-tuning problem in string theory, where the math allows for a nearly infinite number of consistent solutions. If each solution represents a different universe, then we live in one that happens to support life. But this also introduces a dilemma. If everything that can happen does happen somewhere, then how do we assign probability? How do we test predictions? In a universe where every possible outcome is realized, how do we say one theory is better than another? This is known as the measure problem in cosmology, and it's a major obstacle for multiverse models. There's also a human reason why we cling to these theories. The multiverse offers hope. In some universe, we made the right choices. In another, the people we lost are still alive. It's comforting in a strange way. It speaks to our desire for meaning, for second chances, for the idea that nothing is ever truly lost. But comfort isn't science. The multiverse must stand on its own merits, supported by data, not by emotion. And that's the tension at the heart of this idea. It's one of the most exciting, mind-expanding concepts in physics, but also one of the hardest to verify. Still, exploration continues. Telescopes grow more powerful. Quantum experiments grow more precise. And maybe, just maybe, somewhere in the noise, in the data, in the cracks between the numbers, we'll find something we never expected. A glitch in the pattern. A fingerprint from beyond. A sign that we are not alone, not just in space, but in reality itself. Until then, the multiverse remains a shadow on the edge of physics, a theory without confirmation, a story without a climax. But like all great mysteries, it keeps us looking. It keeps us asking. And maybe that's the point. Let's imagine for a moment that the multiverse is real, not just a theory, but a physical truth. What would that actually mean for us? Not just for physics, but for identity, decision-making, even purpose? Start with identity. If infinite versions of you exist, which one is truly you? Are you defined by your choices if every possible one is also being lived? In the many worlds view, you're not a single person, but a branching network of selves. One chose this path, another didn't. Each one is real yet isolated. This idea challenges our concept of free will. If every outcome plays out in some version of reality, then what does choice mean? Do you have control, or are you simply following one thread in an infinite weave? For some, that's terrifying. For others, it's freeing. And what about emotion? The multiverse taps into something deep in our psychology, the longing for possibility. Regret, hope, imagination, they all hint at alternate realities. Stories, myths, déjà vu, dreams, they reflect our instinctive belief that other versions of our lives might exist. Maybe they do. Could we ever connect with those other worlds? Not yet. But ideas like quantum entanglement, wormholes, or even quantum consciousness keep that door open, if only a crack. Some believe our thoughts may already brush against alternate realities, subtly influencing us in ways we can't measure. The implications are staggering. In an infinite multiverse, everything happens. Somewhere you made the perfect decision. Somewhere everything went wrong. Worlds with alien physics. Universes of only light or silence. Utopias and horrors all equally real. And yet, this doesn't make our universe meaningless. It makes it precious. This moment, this life, this you, is the only one you'll ever experience. In a sea of infinities, it still matters. The multiverse may forever remain unprovable, but imagining it stretches our understanding, not just of the cosmos, but of ourselves. We become part of a greater mystery, one not bound by space or time or even by a single reality.